Hi, I would like to start off today's lesson by looking at the area on two functions here. Both functions are rational functions. Matter of fact, if I kind of sketch them, you can kind of see they would even look kind of the same. 1 over x, even 1 over x squared. They're both going to be rational functions in the first quadrant. But the problem is we're going to try to find the area not on a closed domain, but an open domain. We're going to let x go to infinity here. Now it's very important when we begin this to know we can go from 1 to any other number, but we can't go from 1 to infinity. We can't write it that way, because to write it this way, we would say that this is a value, and we know infinity is not a value. You can't count to infinity. I've tried many times. It literally takes forever to get there. So when we want to solve a problem like when we have on an open interval, an unbounded interval such as these, we have to be careful. I'm going to set the problem up the same way. I'm looking for the area underneath this curve. So when I want to find the area, I'm going to take the integral 1 over x dx, and I'm still going to go from 1 to infinity. But the problem is I can't solve it. Now you might be thinking, okay, let me get a separate sheet of paper out here. You might be thinking, yeah, I could write this as just a natural log of x from 1 to infinity. And I would get the natural log of infinity minus the natural log of 1. And that's just 0. And you would probably get the same answer. I would get infinity because the natural log of infinity is infinity. But that's not entirely correct. We can't do this because this does not exist. You can't take the natural log of something that does not exist. So it's improper to really say that. So we don't like to say it this way. So how do we make this proper? Very easy. We have to use limits. And we'll talk about that in a second. Again, this is improper. To make it proper, we're going to use limits. Since I can't be on infinity, I can only approach it. That's what limits allow me to do. So I'm going to write my integral, and I'm going to go from 1, and I'm going to make this infinity b. And I'm going to take the limit as b goes to infinity. So now I'm not saying I'm not going to say it's going to equal infinity. I'm saying we're going to approach infinity. And that makes a big difference. It makes it more proper for us. So when I solve this now, I can use limits to solve this one, and we get from 1 to b of the natural log of x. And now when I apply the FTC here, we get the limit as b goes to infinity of the natural log of b minus the natural log of 1. Again, that's just 0 like we said earlier, and we're left with the following: the limit as b goes to infinity of the natural log of b. Now, remember, we're approaching. And as we approach infinity, b gets really big, and therefore so does the natural log. So it actually approaches infinity. Be careful, that's different. Over here, we said the value is infinity. This is a value. This is saying the value is infinity. We can't have that. That's improper. A value cannot equal infinity. We can only approach infinity. Example I always tell students is, 1, you can count the number of all the atoms in the universe. That's a finite number. You can calculate the expanse of the universe. That's a finite number. Infinity only exists in your brain, in the human brain. We can't equal infinity, ever. We can only approach it. And that's kind of what this is saying, is in this case that the area under the curve, under the function f of x, approaches infinity. Therefore, we say it's a divergent problem. It divergent. It's not divergent. It diverges. And you may recall that the word diverges means it's going to go on forever. It's going to keep growing. It grows unbounded. And that's another way to look at it, is that the area grows unbounded. It never stops growing, just like this lesson. Now, let's take a look at the other one. Same type of problem. Now we would expect to get the same answer because the area here became infinitely large, that maybe this area becomes infinitely large. Well, the only way to test that is to actually solve the problem. There's no real trick. There's some patterns that form, but there's no skill or trick to say, in this case, it's always going to be divergent. So I'm going to set this up. I want to get the area from 1 to infinity of, and I'm just going to write this as x to the negative 2 dx. This is not a natural log, so when I take the antiderivative, be careful before I can do that. Again, this is improper. Almost forgot. I have to change this. This is the limit, and again, I'm going to call that b, as b goes to infinity, and this becomes x to the negative 2 dx from 1 to b. I have to rewrite it. Bad. Good. See, I can't equal infinity, but I can approach it. That's what the limit allows me to do. Taking the antiderivative now, from 1 to b, we get negative 1 over x. And if we apply the FTC, the fundamental theorem of calculus, we're going to get the following. Negative 1 over b plus 1 over 1. I'm subtracting, so it becomes a negative and a negative. And look what happens. I have my limit out here. If I let b go to infinity, here we now get 0. That's interesting, isn't it? So I actually get an answer here. What am I left with? Just 1. So what we're saying is that the area under the curve converges to 1. Isn't that kind of interesting? So this time I get in other words, I get a finite area. Even though the length goes on forever and ever and ever, this is actually going to give me an area equal to 1. Now, we're going to use a lot of these skills later on when we get to series and sequences, okay? Now, if you go to part 2, I'm going to go ahead and take a look at more of a formal definition of an improper integral and take a look at maybe a couple more examples if you like, okay? So I'll see you in part 2.